So we've talked about how a moving charge creates a magnetic field. And today we're going to kind of flip that on its head and talk about how a magnetic field creates a force that affects a moving charge. The fact that electric fields and magnetic fields have come to be thought of as the same thing suggests a strong symmetry between those two things, electricity and magnetism. And today we're going to start exploring one of those. And we're going to we're going to explore more after this. They really are tightly tied together with each other. So I want to think about this magnetic field uh, in comparison to our other fundamental forces. So let's start, and we know that a gravitational field is created by a mass, and it exerts a force on another mass. In other words, the the gravitational mass created by the Earth, that gravitational field, acts on another mass. Okay. Same with an electric field, right? An electric field is created by a charge, and it exerts a force on another charge. Okay. That's our Coulomb's law, our electrostatic force. Well, a magnetic field is created by a moving charge, as we've seen, and it exerts a force on other moving charges. So there's something about the movement of the charge that makes the force magnetic rather than electrical, both in creating the magnetic field and on what it affects. The force on a charge in a magnetic field is called the Lorentz force. And the magnitude of that force field on a charge Q moving at velocity v is this guy. So this is Lorentz's equation. Notice that v, right? If your charge isn't moving, then there's no force. There's no Lorentz force. If your particle doesn't have a charge, there's no Lorentz force. Okay, and then obviously if there's no magnetic field, there's no Lorentz force. What makes this force stronger? Well, we just sort of talked about that. It's the size of the charge, right? How much, how many coulombs of charge are on the particle, how fast it's moving, and the strength of that magnetic field. The sine theta there is important as well, and in a way that isn't particularly intuitive. Sine theta is big when theta is either 90 or 270. It's 0 when theta is 0 or 180. And that theta is the angle between the magnetic field vectors, what direction the field lines are going, and the velocity of the particle. So if your particle is going across a magnetic field, it's going to have a force on it. But if its velocity is in the direction of that magnetic field, there's no force. That means we got to use our right hand some more. But before we get to that, we'll look at our Tesla. A Tesla is our unit for a magnetic field. And if you look at those units, it tells you it's about force, right? The force per how much charge you have and how fast it's going. Now, the direction of your force depends upon two things. The direction of the force depends upon the direction of the magnetic field and the velocity of the charge and the angle between those two things. Okay, so here we use a second right-hand rule, or right-hand rule 1, as we call it here, in which our fingers point in the direction of the magnetic field. And you can think of that as like you've got multiple fingers, right? Well, there are multiple field lines, okay? So kind of keep that in mind. So fingers point in the direction of B. Your thumb, you then turn to point in the direction of the velocity of the particle. And for a positive particle, the force is going to be in the direction that your palm is facing. Again, we'll practice this. It takes a little bit of work to kind of get your head around how that works. So the Lorentz force always acts perpendicular to velocity and field lines, and this has some important implications. One, the force does no work on the charge. Uh, it doesn't change its direction, or I'm sorry, it doesn't change its kinetic energy, because if you think about it, that force is perpendicular to the velocity. It's always perpendicular to the velocity. So what is work? Work is force, how much force is in the direction of your velocity. So there's no work done on the charge. That means you're not adding energy to the charge. You can change its direction, but you can't add energy to it. What it does do is create a kind of centripetal acceleration, because remember, with centripetal acceleration, your acceleration and your force are always directly perpendicular to your velocity. Well, that's what we have here, right? So if our little ladybug isn't spinning around is lazy Susan, but is instead flying through the air with a magnetic field that comes out of the page, then the force is going to be towards the center of her rotation, and she's just going to go around and around. So they create, by their nature, a centripetal acceleration. And if we have a nice uniform magnetic field, that's going to give us a nice circular motion. And we'll see an effect of that in just a second. So consider this field. So when we talk about magnetic fields, you're going to see this a lot. If you see an X, think of that as the back end of an arrow. So that is pointing into the page. Our magnetic field is into the page. If you see just a dot, that means the magnetic field is coming out. And usually you'll see this notation too. Here this is saying your magnetic field is going into the page. So a negative charge here is moving perpendicular to a field. So let's just take one of these points. Let's take this point. So just for fun, if this is what you do for fun, it's what I do for fun. I point my fingers. Yeah, I can see you out there, even though you're listening to this later. I can watch you. Point your fingers into the screen on right next to this guy. I'm doing this here, so I can't actually touch my mouse. Right here. Then your thumb is going to be pointing kind of upwards, right? Your palm now faces the force that would be on a positive charge, which would be outward from the circle this way. Don't forget to use your right hand. And so here our force is in the opposite direction, away from the back of your hand. And we could do that all the way around this circle. At any point, we could say, okay, my fingers are pointing into the page. My thumb is pointing against the velocity here, and the back of my hand is pointing this way. So this is how this particle would just go around and around and around in this magnetic field because of that magnetic force, that Lorentz force. What use is that? Well, let's just talk about one of those. We can combine our equation for uniform circular motion for the centripetal force in that, which is mv squared over r. And we can then take our Lorentz force and set that equal to that centripetal force. So here's our Lorentz force. In a motion like we were just talking about, in a uniform field, that's going to have a centripetal, create a centripetal acceleration here. Then we can manipulate this to get some useful results. So here, if we solve for r, I'm going to move r over to this side and move qvb under here. It's going to get rid of one of those v's because it's going to divide out. And this tells us if I have a particle of a given mass at a given velocity with a given charge moving through a uniform field, I can tell you what the radius of its rotation is going to be. And that is actually what mass spectrometry does, right? You shoot a particle through here with a given charge, you control its velocity, and then you figure out where it's going to hit down here. And if you know where it's going to hit, then you can solve for some other thing that you want to know, usually the atomic mass. You want to figure out what that particle is. Okay, so that's how we use the magnetic field in scientific research.